Hello and welcome, ladies and gentlemen, back to PASCO Laboratories. It's so nice to have you join us. I'm JP, and I'm going to tell you what the P stands for shortly, but I'm going to warn you in advance that today, viewer discretion is advised because we've had some very grotesque viewer mail that I'm going to share with you, and it's going to help you understand where we're putting the P today. So, for anybody that wants to put in viewer mail, by the way, just drop me a line. This is my email address. I'm jkeener@pasco.com. Drop me a line. If we use any of your stuff on the air, we'll be happy to send you a little gift like we'll be sending our online participant who sent in this email. So let me go straight to that email. And remember, viewer discretion is advised, because if you take a look at this picture, it's grotesque. Because Lisa writes to me from Houma, Louisiana, and she said, "You made composting very exciting for my students. Are you equally excited about soap scum? It seems to be a topic discussion on Zoom lately." Well, Lisa, first of all, your bathtub is disgusting. But secondly, don't panic because we've got answers for you. Today is all about soap scum. I put the P in soap scum this week, and we brought in some professionals that are going to help understand why soap scum is so exciting, because we're going to be bringing in soap scum experts Roger and Barbara. And what you're going to come to realize very quickly is that soap scum, though it sounds gross, is all about calcium and magnesium. So let's bring in Roger. He's our first scum expert. Scum expert Roger, welcome to PASCO Live.
The Scum Master here. I have arrived. So
that's excellent. Roger, you've got some insights on this calcium, magnesium, and kind of where it is and how it's found and how it might be impacting Louisiana, where Lisa lives.
Absolutely. You know, calcium and magnesium are just plentiful ingredients as part of the crust of the earth. They make all of the silicates, particularly more so in the ocean bottom. So if you have basalt in your area or diorite, those are things that have been lifted up from the ocean bottom. They'll be right and available where water may pass over and dissolve them. I've given a short map here of where the U.S. Geological Survey has tested thousands and thousands of sites across the nation.
And this is for calcium.
And this is showing where calcium is highly concentrated at the surface. You might see, for instance, in Texas, in the central area of the North American continent, when that was underwater in sort of Cretaceous times, a lot of calcium was being concentrated by clams and coral reefs. And so that's there.
And not a big surprise for my friends that live down in South Florida. When I'm taking a look at this map, I'm seeing the calcium. Of course, South Florida is an exposed coral reef. The calcium carbonate there is strong, and so that is strong calcium concentrations. But in Lisa's case, there in Louisiana, I'm not seeing a lot of calcium. So let's go to the other scum culprit. Let's take a look at magnesium.
All right, magnesium is scum culprit 2. That is coming straight from those soil components. If you have that kind of rock material, a lot of soils are being deposited that are breaking down out of the mountains and could be, part of the reason that that's available. You'll notice all along the Gulf Coast, because of the rain, especially in this last week with the hurricanes, you can see that water is washing a lot of anything that's soluble out. But even if it's still just a little bit, and like we saw, proof enough, there was enough so that it would create a precipitate of that calcium with your soap. And really it's a reaction with soap and those +2 ions in your water.
So scum sounds gross, but it's actually kind of exciting. We're looking at calcium, we're looking at magnesium, we're looking at it how you can see it in your water. And I think what we'd really like to do is let for our teachers and our folks at home find some ways that maybe they can explore this calcium, magnesium, the word that we call it is hard water. If you've got hard water, if it's got these things in it, you might like to find some ways that you can explore this at home. And then we might even like to find some ways that you can explore this in the lab. So whether it's hard water or soft water, you need to know more about scum, and that's why we're going to bring in the queen of scum. Let's bring in Barbara. Roger, why don't you come over here? Let's bring in Barbara, and let's learn about scum.
Fantastic. My very capable lab partner and a colleague in crime. Barbara, let's jump in and let's see what we can do to show you is how you can do some great experiments in terms of finding out whether your water's super hard or soft and what that can be done about it.
Sure. I'm happy to share my at-home scum experience with you. So this is something you can do at home. This is a qualitative way, or a way of measuring with your senses without equipment whether you have hard water or not. And maybe even a comparison of how hard your water is compared to maybe a different source. So we're going to, I guess we'll start with the tap water here at PASCO headquarters in Roseville, California. You need just your sample of water, and this is Castile soap. This is a natural soap or a true soap, soap that's made with something basic like sodium hydroxide or potassium hydroxide and a fat.
And I'll point out what those molecules look like here shortly.
Right, and we'll show you the chemistry behind this, but we're going to keep it top level here for the first demonstration. I'm just going to get some of this Castile soap and drop it into this sample and then stir. And you might be able to tell it's slowly turning white.
Yeah, it looks kind of pearlescent, or, you know, sort of like a pearl.
From clear to white, that means we are forming a precipitate in this solution. What's happening, and Roger will go further into detail on the chemistry, is something in the soap molecule is reacting with something in the water. Guess what that something is?
Soap scum.
Calcium and magnesium are reacting to produce that soap scum. You're looking at soap scum there in its infant form. Well, let's take a look at what happens when you don't have soap scum. So Roseville has somewhat hard water because we did get a precipitate. We got a reaction. Let's look at the same source, our Roseville water, but filtered through a carbon filter. Same water source gone through a filter with some soap added, and let me stir.
This would be like a water softener at home. It's actually a ion exchange column where it's good at taking out those plus ions.
So I notice, you notice it's not turning white. I see no precipitate. It's staying clear. I just have a few soap bubbles at the top there.
I really do see that this is a much more milky sort of look to it than that one is now. So that's a great comparison.
Right. So there are no, or such a small amount of calcium and magnesium ions in this water sample. It's soft water, and we can tell because we did not get that precipitate reaction. Let's look at a sample of mineral water that I got at the grocery store where they add on purpose additional calcium and magnesium ions.
For taste, yes.
Right, for taste and for your health.
Yes, indeed.
So let's add some soap to that and compare with our other two samples. And right away, before even stirring, you can see it's quickly turning white.
Oh yeah, look at that.
Lots of precipitate. Let me put it right next to the Roseville water. As you can see, qualitatively, there's more calcium and magnesium, maybe even iron ions in here. We can't measure how much with this method, but we do have methods to test that. And finally, here's just down the street from Roseville is where I live in Carmichael, California. And let's compare Roseville tap water with Carmichael tap water and see if we can see a difference. Okay.
Oh yeah, there you go.
So yeah, I have hard water in my house, and it's slightly more calcium and magnesium concentration than here in Roseville, but not as much as the mineral water.
Now, Barbara, you've just shown us that, you know, really you can kind of see the differences in where there's more calcium or magnesium in the water to make those hard water solutions. If you want, I'll get into just a second a way that you can literally be more quantitative about it. But let's talk a little bit about what that looks like at the molecular level. This is cool because this will come together, and we do sell little molecular model kits like this that you can use in your classroom. This is a picture of fat. Okay, so fat is where we start from for soaps. I mean, that was the original. They boiled fat in lye. Lye is a lot like Drano, and that's why we pour Drano down the drain as it gets and breaks up those fats. And when it does, I'll go ahead and break this away. Here's one fat. It's called a stearate, and that's going to come together with our sodium hydroxide. I'll put that together with this guy, and we'll put them right in here. So that's sodium. It's got another one here. Each fat molecule has three sort of arms in there, and I'll pull this last one off. This is the triglyceride head that's on top, and that's what they measure if you're looking at your heart for the sort of materials in your health. Each one of these is normally associated with one sodium on here, and what makes that cool is this top part here is charged. It's an ionic compound. Sodium is +1, the carbonate or carboxyl group is a -1, and so water loves this and would love to grab onto this. Now, here's where the cleaning part comes in, is this back part is really just, it's a hydrocarbon, or it looks a lot like oil or grease. And so this molecule is great to go along oil and grease that's on your hands or on your skin. When you wash that off, water grabs the top and pulls that away. And so that's our cleaning action that happens in terms of soap, and why it was always such a great molecule. The way they get it is boil fat with a little bit of ash from the fire, and that would create and break down those fats into these great molecules. Trouble comes along when now, if you've got hard water like calcium, it's +2. So not only does it like this soap which has a +1 charge, but it still has another charge on here, and it ties these heads up. What happens is these two get tied together, and what do we have that's left? Really just this greasy or oily sort of like substance. It doesn't dissolve, and so it'll precipitate out, makes that white sort of compound there. And it also sticks to the sides of your tub, and it becomes gross. So that's where you have to get in there and clean it with some materials. But if we want to then study how you can tell quantitatively a little bit of what's going on in terms of your water, here's a great way at home to be involved. You can just find 10 little sort of test tubes, or if you got just little vials that you can get at Michael's or any of those kinds of places. I'll put this right out in front. What I did is I laid these down against the wall. I put a marker on there and just marked them evenly so that we have an even amount. The key is just to put an even amount of liquid in each of these test tubes. Now, if you're at a school and you've got, for instance, a graduated cylinder, one way you could do that evenly is to actually pull out 3 milliliters, because I poured out that amount and found out, oh yeah, that's 3 milliliters, with a nice eyedropper, and I'll fill this last one up just because we need to make sure that one's in there too, so you can see this process. And I'll just pull this down until I get from 10 down to 7 milliliters, and that's a nice, accurate way to do this. So those are two different ways that you could fill these. Now, one of my students has done this for a science fair project many, many years ago, and she did a great job. She went right down to the finals at the state level because she was very systematic. So I loved what she was able to do. Last thing we're going to do is just take some type of soap. Now, as long as it's the same concentration for your whole experience, this is just raw soap right from the store, right?
Yes.
Awesome. So all I'm going to do is just put 1 drop in each one of these. And then slowly mix that concentration up. I'll start from one side, and we'll just put 1 drop in each one. There's 2 in that one. I'm going to put my finger there. There's 2 in that one. 2 in that one, 2. Well, I'm just going to put 2
Let's
in the
do 2 in all of them.
rest, and then I'll put 2 in that one, 2 in that one. Oh, now there's 3. I'm going to keep the finger there. That's all right, because now I got to put 3. So here I'm going to put 1 more there. This one's taken care of. There's 3, 3, 3, 4, 3, 3, 3. I'm going to go to the 4th one, a 4th drop, 4th drop. Oh, that's got 5. Skip this one. There's 4, 4, 4, 5, 5, 5, 5. I'm getting better. 5, 5. Now I go to 6 one. 3, 4, 5, 6, 6, 6, 6. Get that little guy in there. And I did an extra drop in that last one, so I'm good there. So I'm on the 7th. 1 drop here, 7. Ooh, that one's taken care of, that one's taken care of. So just 1 drop here. Now they each have what they need. I'm going to now go on here. 8, 8, 8, 9, and I got 2 drops in that last one. So you get the idea. Of course, you're going to get a little practice. What I've done now is I put an equal amount, a graded sort of column here. I'm going to shake these. If there's excess soap in there, all the calcium here has been taken up and has been tied to a soap. So not enough soap to leave sort of bubbles. So the soap is all taken out of that amount. That's 2 drops. Here's 3 drops. I'm just starting to get kind of soapy look to that. And I think the rest, if I shake these, are all going to be soapy. And what's great is that now you have, oh, let me do that on all of these. Soapy solutions. But at this point, we had basically 2 drops worth of soap to tell us what amount of calcium and magnesium are in your water. So they just went to several different water sources and were able to do a quantitative study using just drops of soap with an eyedropper and an equal amount of starting water. It was a great project for students.
What did they measure in this experiment?
So they're actually measuring the magnesium and calcium ions in the water.
Did they use a ruler to get the soap bubble height, or how did they?
They just looked for the presence or absence of soap,
okay.
And then the quantitative amount was the number of drops that they put into each of those test tubes. And so at home, like I say, it may take a little practice. You may find that you've got to, for instance, use a lot more water because it's already too concentrated or isn't that concentrated. If you're along Gulf Coast, like we saw in those pictures, you may not have that much calcium in there, but and so you'll have to think different ways to sort of measure that, maybe using more concentrated or start with 5 drops of soap or something. But once you get the hang of it, you can really use it as an analytical technique. Now, as you said, maybe you're at school and you want to do some advanced sort of sort of measurements, right?
Right, so we showed you a couple of at-home experiments, and now we're going to shift into in the lab. And these last two experiments that we're going to show are both based on the How Hard Is Your Tap Water lab investigation out of the Advanced Placement Chemistry, or rather Advanced Chemistry Manual. So the first method, quantitative method I'm showing, is the filtration method. You get 0.1 molar sodium carbonate and mix an equal volume of 0.1 molar calcium chloride. And this is a stand-in for a water sample, but we're using a known concentration of calcium in this water sample. So you would expect the calcium to replace the sodium, and we definitely see there's a precipitate there. Calcium precipitating out to make calcium carbonate. So with this method, so you finish stirring with the stirring rod, and then you take your time filtering your solution through this filtration apparatus, and you've got to wait for everything to separate physically. You've got to keep stirring this solution and pouring it in your filter and waiting for this gravity-fed process to happen, this gravimetric analysis. It takes time. So not only do you have to wait to filter the whole thing out, but then you have to wait for your filter paper to dry, either 24 hours by air or a few hours in a drying oven, and then
Great skill builder for your students to be careful, to make sure that they're transferring all these materials. So it's a good skill builder in that advanced chemistry sort of realm.
right. So it will take more time. So build that into the lab period. That this is time consuming, and if you don't have as much time, you can switch over. Let me quickly talk about how you would analyze this. So you would let the filter paper dry with the mass of calcium carbonate precipitate on it, and measure the mass of calcium carbonate and determine the concentration of calcium ions in that in the water sample, the calcium chloride sample. So because we're using a known amount of calcium chloride, we can also do a conductometric titration, which is another way to analyze, using drop counter.
So there's a great alternative to the gravimetric test, where we're weighing the paper and seeing how much it's increased after you've dried that paper. Now what we're going to do is we're going to use a drop counter here with a conductivity sensor that's on the side. One of the things we'll do is to make sure that we keep that solution stirring. I'm going to go ahead and turn on the stir plate here. There we go. Make sure that's nice and getting a good stirring action. We're going to drop in the chlorides into this calcium solution down there. So they'll, again, just like that, we're still making the same calcium carbonate. So we're putting a calcium chloride into that solution. It's grabbing the chloride and falling out. But we're going to measure the concentration of conductivity. So as long as calcium chloride's there, they can be conductive. They're ions and can move. But once it hits the carbonate, they become solid and they don't conduct electricity. So now that my drop counter's on and my conductivity is going, I'm going to go ahead and run a little movie here that we're going to watch some data start to be collected. And let me see.
Okay, so this is that same reaction. If you look in the beaker there, you can see, maybe you can see.
Yeah, it's forming a little cloudiness, and then it redissolves as it's being redispersed.
Right, and if you're looking at the data, you can see that the conductivity is dropping inside the beaker because those calcium ions and chloride ions that were free, the calcium ions are getting tied up when they replace sodium coming out of the sodium carbonate, and we're getting calcium carbonate precipitate, soap scum, in the beaker.
Now, this is going to take a lot quicker if you're working with your students. What's nice about that is that it takes less time to gather the data, and you're giving your students a lot more time to think about what that data means. Usually you'll do a titration, probably in acid-base kinds of chemistry, and what's nice is that if you can use titration as a different kind of a technique, in this case for non-soluble ions, they get sort of exposed to that same technique, but used for, like we're saying, sort of a precipitation reaction. They can start to then be more comfortable when they get down to the electrochemistry at the end of the year for organic reduction potentials. All of those kinds of things are great because you're giving them skills a couple of times in the year to build those AP sort of level skills.
Right, and keep in mind, in this experiment, on our design, the sample there is just calcium chloride. It's a known concentration of calcium. However, when you use tap water samples, first you've got to boil them down to concentrate the sample, but also when you have your precipitation occurring, it's not just the calcium carbonate precipitate, it's also magnesium carbonate. So when you do a tap water sample, it'll look the same, but we've got we've got the measurement of both of those calcium and magnesium ions.
Yeah, and you'll know if you're in an area that has, not very hard water. It's hard to wash the soap off, and we used to call that when we were growing up slippery clean because it was so long to wash out your soap. But if that's the case, then like you said, you'll have to concentrate by boiling down your solution so that you can concentrate enough to see these. But all of those instructions are in the handout.
That's right.
As a matter of fact, for analytical skills, once we collect these, we're going to go ahead and
stop our data collection so we can look at some previously collected data.
Yeah, absolutely.
Yeah. Okay.
Okay. Let me go ahead and stop that.
So we did a titration previously with the same setup, and we just put 15 milliliters of calcium chloride in the bottom beaker and added enough distilled water to cover the end of the sensor, and dropped in 0.1 molar sodium carbonate. So same setup. Here's my data. The conductivity dropped, and suddenly at the bottom here, I've got volume on the x-axis. Suddenly the conductivity starts to go up. So that's because the calcium ions are free in solution, but they begin to react and form a precipitate. Therefore, the conductivity is dropping because there's less calcium ions to conduct in there until we get to a minimum there. At the minimum conductivity, we can assume that's where there's the maximum product calcium carbonate. That is the soap scum. So we can use the analysis tools in SparkView. I'm just going to select the statistics tool and get the minimum value out of all this data. So the lowest point it's telling me is 5198.7 conductivity units microsiemens per centimeter. So if I find that data point on the line, 5198.7 down here, it tells me that the volume at that conductivity is 13.54 milliliters. That's a V, the V of my titrant sodium carbonate. I know the molarity of sodium carbonate, I know the volume of sodium carbonate, I know the volume of calcium chloride. I can solve for the M concentration of calcium chloride. And once I know the concentration of calcium chloride, I can do some stoichiometry and work my way and get the mass.
Yep, the carbonate tells us how
calcium.
much calcium was there.
Yes.
Absolutely. Well, these are fantastic, and what I'm going to do is thank you so much for helping us walk through some of these labs.
Though, we've got a question coming in from Richard in Folsom who says, Barbara, do you have this lab written up already? Where can I find it?
Yes, find your way to the experiment library on PASCO.com, and you can just search how hard is my tap water, and this experiment will come up.
So those are accessible to anyone that wants to. Just search on PASCO.com under their resource library. I'm going to move over so that we can get JP to come back.
And could anybody be any more excited about Scum? I mean, is it even possible to be any more excited about Scum? And so Lisa, who wrote in that question, we're thrilled that you wrote in that question. Lisa, I'll be sending you your very own I Love Chemistry bumper sticker and a conductivity sensor so that you can measure your hardness of water to determine why you've got so much scum, and you can share that with your students. Do all of these experiments with your students so that they can measure the amount of hardness in their water so they can figure out why they are getting scum. But yes, we're excited about Scum. We're excited about a whole bunch of things you can study in chemistry. And Roger, you've actually put together a kit, a lab station that allows people to investigate all these great things. You want to tell me a little bit about this?
Absolutely. So we've given you that awesome opportunity to do some study at home things just with what you can find around there. But if you're at a school, you'd probably like to be able to have a set of equipment that gets you a good start on lots of experiments. And what you're going to see is in the sort of getting starter lab station, you'll have enough that you'll get experiments that are typically done in the earlier parts of the year. From temperature experiments, pressure experiments, gas laws. It does come with that molecular model kit that you saw us working with, and so that students can really get a hands-on sense of what goes on early on, 3/4 of the way through your chemistry year.
And we call this part of our 10-10-10-100 package,
That's right?
Because it comes with 10 ready-to-use labs right here in this nice little lab book, 10 ready-to-use labs. We open them up and they're ready to go. But these labs also come with 10 data sets, data that's already been collected that you can post on your LMS, share with your students, let them do the lab. We've got the lab, we've got the data. We even have 10 videos of Roger and Barbara doing these labs that go along with it, and 100% of all of the resources available to you in our library. So we call it the 10-10-10-100, and that's just for the basic package. Roger, we can go a little bit more advanced like we did today, correct?
Right, and then while we have all those videos to support in this crazy time where if you'd like your students to still be able to see those when they're not in school, oh, that's okay. Some of the advanced labs that you're going to be able to do is to take a look at colorimetric titrations or seeing different kinds of reactions that happen by color. The drop counter that we saw in this experiment is available here. We've got the voltametric sort of analysis if you're doing things from oxidation reduction, and then a condenser as well. So those are things that are either the AP classes you're going to really be focusing on, or if it's towards the end of the year, second half of your year, you can find that the extension lab station would be a great way to get started. Even if you're just using one from up front, it's a great tool for you, and we hope that gives you a way to put some of these tools in your classroom.
And the really neat thing is, with all of these labs that we're talking about, even with the AP labs, you can go to our collections. You can take a look in our library. These AP labs are available to you, but you can even take a look at our AP lab manual, our AP chemistry lab manual, our advanced chemistry lab manual. Take a look at the collection that we put together there for you. You will find this lab, but you will also find 10, 12, 15, I forget, Barbara, how many? 14? 15? I believe 15 advanced labs that you can find right there in our collections. Just go to our advanced placement, our advanced chemistry manual. You'll find all of these activities there. But I want to also put a shameless plug. If you like what you saw today with Roger and Barbara teaching this stuff, I want you to know that we also have an opportunity for you to visit us at the PASCO Academy. And that's pasco.com/pasco-academy. And you can see 15 weeks of Barbara and Roger doing direct instruction for you, the teachers, so it's great professional development, but also providing these labs direct to your students. So if you would like for them to teach your students, like you saw them doing today, and I think doing a great job today, showing what we can do and then sharing that data with your students, take a look at the PASCO Academy. And know always we've got a great promo for you. And of course, we do have a great promo for you this week. All you have to do is reach out to our own Isaac Martin and say, Soap Scum. Because today is all about Soap Scum. And reach out to Isaac and say, hey, Soap Scum, I want a good deal on this stuff. And he's ready to give that to you. He's ready to give you a great deal on these chemistry sets, both the basic and the extension in these lab stations. And of course, if you don't have an Isaac Martin, don't panic. You've got somebody that's with you internationally in over 100 partners that are available. And do remember, like I said, take a look at our PASCO Academy, get a good feel for what's being taught here, take a look at how they can do it for you. We certainly love to hear from you. Just drop me a line. I'm Jay Keener at pasco.com. We are certainly happy that you joined us today. Roger, thank you very much. Thanks to Barbara, the queen of Scum, for joining us today. And we wish all of you the best of luck, great teaching, and good day.